Let's look at a circuit in which we have a C to V EMF that we're going to look a battery. And here we have a point, let's call this A and this B. And we know that the terminal potential difference for an ideal battery is equal to the electromotive force. Now remember, electromotive force is not a force, it's the energy per charge in moving a charge across the terminals from, this is what we call the negative, to the positive. So this is our ideal battery. There's no resistance in this battery. And now we want to connect this battery to, we could think of it, these are our terminals. And we connect this terminal to a wire, and in that wire there's a circuit element which we're going to refer to as a resistor R1. And here, let's call this point C. Actually, we'll call this point D, and this point here C, and that point D. And I'm just going to connect it to another circuit element. And again, this another circuit element, it may be a light bulb, it may be a rolled resistor of some type. This will be a second resistor, R2, and we'll come back to where we are. Here's D. I'm going to call this E. On the other side here, F, and then I'm back to A. Now, when we analyze circuits, we want to talk about the potential difference as we go around this closed path. Now, we know in electrostatics that the line integral of d dot ds is 0 around the closed path. And recall that when we talk about potential difference between any 2 points, V, say D minus V of C, that's the integral from C to D of the electric field in going from one point to another with a minus sign. So the fact that all of the potential differences around a closed sum up to 0 is just a statement that the line integral of E around a closed path is 0. So that fundamental law of electrostatics is translated into the statement that the sum of the potential differences around a closed path, I, however many we have, is 0. And now we can also, we want to apply that to this loop. But what's important to realize is that here, our wire is, we're assuming that this connection between B and C, this is a resistanceless wire, R is essentially 0. And so that tells us that the potential difference at C is the same as the potential difference at B. The potential difference at E is the same as D. The potential at F is the same as A. And what we see is that the potential is increasing as we cross the C to V EMF, and the potential is decreasing as we cross a resistor. And it decreases as we cross the resistor, because in this case, the current I will flow, and I flows from high potential to low potential. And so as we cross that resistor, the potential should drop. So let's just make a graph and see what happens with the potential. As this is not in time, but it's in space. And we'll start at our point A. Now, we'll call the potential here at A, V equals 0. So we're arbitrarily going to call that our 0 point. And so when we go from A to B, we're crossing the C to V EMF, and our potential is rising to a point E. So we get a potential increase at B. Now as we go from B to C, that's along our resistanceless wire, and the potential is staying constant at C. Now when we go from C to D, we're crossing a circuit element, the resistor, and there's a drop in potential here, and let's just make a note of that. The potential on the lower side of the resistor minus the potential on the higher resistor is I R1. That's Ohm's law. Now we go from D to E. So here's E. Potential is constant along our wire. Again, we have another potential drop. Notice that when we go from E to F and F back to A, I'm just jumping ahead a little. These are at the same potential, and that's back to our 0 point. And so when we're going from E to F, if the sum of the potentials around the closed path is 0, we're dropping down to 0. And this is a graphical representation of the idea that the potential drops around the circuit, this single loop circuit, are 0, and it amounts to the following statement, that plus E minus I R1 minus I R2 is equal to 0. And that's an example of the idea that the line integral of the electric field around a closed circuit path is 0, where there's a steady current flowing.